So where we had left off was we were talking about the vector formulation for backprop. We've already worked out the simple arithmetic for backpropagation where every variable was individually handled. But it's simpler to think of the process in terms of vector operations because the arithmetic is simpler and fast matrix libraries make operations that much faster. And so how do we do it? This is what we do. So we can we can write a new variable zk. The subscript k represents the layer, which is simply a vector of all of these affine terms, right? Similarly, I can write a vector variable yk, which is simply a vector of all of these activation output terms. And then we can write the bias. Remember, each of these neurons has a bias, right? So all of their biases can now also be written in a vector of bias terms. Now, there are weights connecting these guys, the bias in the previous layer to the bias in the next layer, right? How would we write the weights? So if I think about this, again, so y subscript k is the output of the activation at the kth layer. Z subscript k is the vector of affine values at the kth layer. B subscript k is the vector of biases for the kth layer, right? So the output of vectors for the k minus 1th layer, the output of the neurons in the k minus 1th layer would be a vector y subscript k minus 1. So you would have y k minus 1 equals y1 k minus 1 through whatever yn k minus 1, right? And so now if I look at z1k, z2k, zmk, what is this? I can write this as, so these are y1 k minus 1, y2 k minus 1, yn k minus 1. So how is this first term computed from these terms? Can anybody tell me? What multiplies y1 over here? Ketan. What multiplies y1 over here?
wk.
W?
K.
Yeah, but no, what multiplies this specific variable when I'm computing this?
Oh, that specific variable. It's W1 from K.
1K,
K,
right?
yeah, 1K, yeah.
Okay. What multiplies this variable?
W12K.
1, 2?
K.
The notation was it's connecting
Plus,
2 to 1.
Yeah.
W21K.
Oh.
W21K, right?
Oh, yeah.
And the next one, so this is going to be all the way to WN1K, correct? And then what about Z2? What are the weights?
W21K.
No, it's not. W21 is going from 2 to 1, right? This is going to be, I'm connecting what multiplies Y1 to give me Z2.
Yeah, W21K.
W21 would be connecting, is this guy.
Oh, W12K.
W12K, correct?
Yes.
This is going to be
W22K.
22K. This one's going to be, final one is going to be
N2K.
N2K, correct? And then similarly for the last one, what's that going to be? This one?
NM.
That's going to be W.
NM.
1NK.
1MK, W2MK, all the way to WNMK, correct? So this is my weight matrix. And then I'm also adding a bias. What is the bias that I'll be adding for the Z1? 1? That's going to be B1K, right?
1K.
1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. 1K. For Z2, the bias is going to be B2K, and so on. So this is going to be BMK. Right? That makes sense to all of you? Yes, no. Say something, guys.
Yes.
Okay, so if I were to
Please,
write this, yeah.
For the W, I think the first index is the row and the second is the column.
The
Right. So
first
if
index,
you
so the indices are, the first index is, the second index is going to be the row. The first index is the, right. It gets a little confusing because of that. In that the kth row tells you the weights that contribute to the kth affine term, right? So the second index is always going to be, I mean, L. I'm overloading the notation. But anyway, you're right. So if I want to write this in vector notation, this is ZK equals WK, and see the nature of the weight matrix times YK minus 1, because these are all the K minus 1, plus BK. Correct? Is this making sense?
yes.
Everybody?
Yes.
Okay. And so you have this lovely thing that I can write the entire layer using just these two simple operations. ZK equals WK YK minus 1 plus BK. And YK itself is simply this activation functions over here applied to ZK, which I can think of as a vector function for all practical purposes, right? You guys with me? Is this making sense?
Yes.
Right, and so here's what I could do. I can just set Y0 equals X, my input. Z1 is simply going to be W1 Y0 plus B1, right? This is just following the same format where we say ZK equals WK YK minus 1 plus BK, right? And so then Y1 equals simply F1 of Z1. Down here, I'm writing the complete operation, but you can ignore it because then Z2 is W2 times Y1 plus B2, right? And then Y2 is going to be just F2 of Z2. So what will Z3 be? What's Z3?
C3.
Because I have the Y2s, right? I want to compute the next Z's. What will Z3 be?
It will be W3,
W3,
Y2,
Y2
Y2 plus B3.
plus B3. So lovely, right? So simple, right? And what's Y3?
F3 of Z3.
F3 of Z3. So wonderful. And so on, right? And we can go all the way to the end, where you get Zn equals Wn Yn minus 1 plus Bn, and then you apply an activation. And since I'm writing the entire thing in vector format, you don't really distinguish between scalar and vector activations, right? It's just an activation function which could either apply individually to each Z or communally, right? And that's the output. And so now, here's the entire forward pass. It's so simple. I just say Y0 equals X, and then I'm just looping through the layers. At each layer, I just compute ZK equals WK YK minus 1 plus BK, and YK equals FK of ZK. And then the final output is the output of the network out here, the final layer. So this would be my pseudocode. So trivial, right? So is everybody with me so far?
Yes.
Okay. And so we see why writing this as vectors makes things very simple in the forward pass. Where we get tangled up is when we begin doing the backward pass, right? So before presenting the backward pass, I'm going to give you some more calculus. Remember this thing. Even if we saw this for scalars, right? If y is a function of a vector, then we said that delta y is the derivative of y with respect to z times delta z. Remember this? Remember this, guys? Yes, no? Right? And so if z is a r cross 1 vector and y is a scalar, what is this? What would that be?
1 by R.
It's going to be 1 cross r. Otherwise, you won't be able to multiply things, right? And its transpose is what we call the gradient. So far, so good, right? I can still write this way. I can still write my influence diagram like so, except now x is a vector, y is a scalar, and this is simply going to be integral of derivative of y with respect to z. If x is a column vector, this is a row vector. That makes sense? I'm still drawing the same influence diagrams, nothing changed. Yeah? You with me, folks? Okay. Now, when I have a vector function of a vector argument, y is a vector now, right? Z is a vector. So y has many components, z has many components. The number of components may not be the same in both. The same math holds. So when I'm speaking of the derivative of y with respect to z, it's basically this multiplicative term which multiplies delta z to give me delta y, right? So if y is an m component vector and z is a d component vector, what is the size of this derivative? Anybody? Here,
M by D.
it's got to be m cross d, right? Otherwise, things will not match. I mean, here I've got I'm using different notations above and below. So the slide is slightly messed up, but you got it, right? That derivative has to be m cross d. Everybody with me here? Okay, so what is that matrix? It's very simple. Let's call the Jacobian, right? So the way to think about it, let me add a discard this. Keep it here. So let me add an empty slide over here so I can explain this math, this Jacobian, which is okay. So here's what I had. I had y1 through ym equals some matrix delta, right? Delta y1 through delta ym equals some matrix times delta x1 through delta xn. X d is how I wrote it, right? Well, let me call this n for now. This is what we had for y equals f of x, where both of these are vectors, right? This was the derivative, correct? You guys with me? Yes, no. Okay. Now again, note that y1 through ym is a function of x1 through xn, correct? Now consider just the first term. What is delta y1? This is in fact m independent functions. The way to think about it is that there are m independent functions, one for each y, right? I can think of x1 through xn, each of these independently affecting y1 through yn, correct? Does this influence diagram make sense to you? Right? So if I just consider y1, the first variable, what is the derivative of y1 with respect to the x's? What is delta y1? When I've got
x1, delta
x1 through delta xn. So what multiplies delta x1? To get this. Guys, just focus on this one term. What multiplies delta x1 when I'm trying to compute delta y1?
With respect to
It's going to be partial of y1 over partial of x1, right? What multiplies delta x2? What
y1
multiplies?
over s2.
It's going to be partial y1 over partial x2. It's going to go all the way to partial y1 over partial xn, right? What about delta y2? What multiplies delta x1?
partial y2 over partial x1.
Partial x1. This is partial y2 over partial x2. Partial y2 over partial xn, right? And so delta y m is going to be partial ym over partial x1, partial ym over partial x2, partial ym over, come on, partial xn, right? And so this is my matrix equation, correct? Is this making sense? Guys? So this is your Jacobian. The Jacobian, each row of the Jacobian is basically the derivative of the corresponding variable with respect to the axis. So you can think of this Jacobian just as y is a vertical stacking of the, just as y over here is a vertical stacking of the individual y's, the Jacobian is a vertical stacking of the derivatives of the individual y's on top of one another. That makes sense? Yes or no? Right. So we're going to use that, right? There's your Jacobian. The first row is simply the derivatives of y1 with respect to the z's, when y is a function of z over here. The second row is a derivative of y2's with respect to the z's, and so on. Right? So why do we sometimes put a transpose for the, these are not the gradient, this is the derivative, this is not a gradient. The gradient is always a transpose of the derivative. The derivative of a column, of a scalar with respect to a column vector is a row vector. So it's in a completely different space. Row vectors and column vectors don't live in the same space. To bring that into the same space as the original data, you have to transpose it and make it a column vector. So the gradient lives in the same space as the z. For that, you have to transpose the derivative. Does that answer your question? Right? And so the transpose of the gradient is the derivative. The gradient is the transpose of the derivative, right? So, and now, if I have scalar derivatives, each y is a function of only the corresponding z, doesn't depend on the remaining z's. So this Jacobian is going to be a diagonal matrix, right? Where the diagonals are the derivatives of the individual activations. You guys with me? Yes or no? Yeah, okay. And when it's a proper vector activation, the Jacobian, each y is going to be a function of every z. And so the Jacobian is going to be a function of all of the partial derivatives, which will not necessarily be zero. So far, so good, right? And so now let's get to this affine function. Remember, we're computing z equals, we had z equals wy plus b, right? I'm not putting the layer index over here. But then we said z equals wy for plus b, correct? So what is delta z? How does delta z relate to delta y? Anybody? How does delta z relate to delta y, given this? Can you tell me? Let me do this. Z plus delta z equals w times y plus delta y plus b, correct? If I increment y, z increases. Does it not? Yes or no? Right. So how does delta z relate to delta y? Based on this. Just look at the equation. Pardon me?
W delta y.
W delta y, right? Can you not see this? Z is taken care of by y. So delta z must be taken care of by delta y. Delta z is w times delta y, right? And so the derivative of z with respect to y is going to be, what is that? Remember, delta z is the derivative of y with respect to z times delta y. That's going to be w. This is the Jacobian. Make sense, everyone? Yes, no? Did this make sense? Okay. What is the derivative? If I perturb delta B? If I perturb B without changing Y, how does Z change? What is the multiplicative factor? Over here.
Identity matrix.
It's an identity matrix. So what is the derivative of Z with respect to B?
Identity matrix.
That's an identity matrix, correct? So everybody with me so far? Yes, no. Okay. I have to make sure that you're hanging on, right? And now I can still use the same chain rule as before. But this gets more interesting when I'm looking at the chain rule, right? I had X influencing. What is the influence diagram over here? What influences what? What's the influence diagram? X to Z and Z to Y, correct? So what is the derivative here? What is the derivative on this edge? Tell me. If these are vectors, I can generally write this as vectors or scalars. It's going to be the derivative of Z over X, but with respect to X, correct? You don't write dy over dz over dx because we're not claiming these are scalars. Right. So what is the derivative here?
Derivative to y to respect to z.
This is derivative of y with respect to z, correct? So this means delta y equals the derivative of y with respect to z times delta z, right? That's looking at this portion of the influence, right? Yes, no?
Yes.
Okay. And delta z in turn, from this guy, what is delta z? What is delta z? Folks, from this part of it, what is delta z? From here. What can you tell me about delta z? It's, someone give me an answer. Vibha, what's the answer?
It would be the Jacobian once again.
What was the general rule for the influence diagram? Rohan, can you tell me?
Chain rule.
What was the influence if I had anything of this kind, x, y? How did delta y relate to delta x?
You can say that a change in x affect y.
Yeah, so what was the relationship anytime on this? What was, if I put an alpha on the edge, how did we say delta y related to delta x?
Delta y equal alpha delta s.
Okay, now from this, what can you tell me? What is delta z? Use the same logic, right? What is delta z? Guys, this can't be so hard. It's going to be, it's not dz over dx, it's the derivative of z with respect to x times delta x, correct?
Yes.
Vibha, does that make sense?
Yeah.
Okay, and so now I can plug this delta z in here, correct?
Yeah.
And so I'm going to say delta z of y, derivative of y with respect to z, times the derivative of z with respect to x times delta x, correct?
Yes.
That makes sense? Yes or no? And so then what is the derivative of y with respect to x? What is the derivative of y with respect to x? Aryan?
Delta z times gradient of y with respect to z.
It's going to be this term, is it not?
Yeah,
It's there on the screen, correct?
yes.
Yes or no, guys?
Yes.
Okay, so the derivative of y with respect to x is the derivative of y with respect to z times the derivative of z with respect to x. Can I change the order?
No.
No, because then it's not going to connect up like this, right? So it's going to be the outermost term first, and then you're going to keep going backwards. So let me give you another example over here. So suppose I have something of this kind. Let me just pardon me for these things, but I need new slides. And this is taking longer than it should, but I'm just trying to convey this business of the derivatives out cleanly, right? So suppose I had x, y, z, w, right? What is the derivative of w with respect to x? What's it going to be? Anyone?
Yes. It is.
Go ahead.
Yeah. It is the derivative of y respect to z multiplied by the derivative of z respect to y multiplied by derivative of y multiplied respect to x.
In this order, correct? Did this make sense, guys?
Yes.
Going this way, correct? Beautiful. That's very simple. And when you draw the influence diagram, it's obvious why this must be so. Yeah. And so it applies to any case, right? If y and z are all vectors, then all derivatives are Jacobians. So the Jacobian of y with respect to x is going to be the Jacobian of y with respect to z times the Jacobian of z with respect to x. You can check it out, right? On the other hand, if d is a scalar and y is a vector and z is a vector, the same thing applies. The derivative of d with respect to z is going to be the derivative of d with respect to y times the derivative of y, Jacobian of y with respect to z. So the outermost guy becomes the first term. The outermost guy, so this literally means z influences y influences d, correct? That's what this equation means. And so when you write the derivative, the first term is going to be the derivative of d with respect to y, and then the second term is going to be the derivative of y with respect to z, okay? And here's the interesting thing, if you will check the sizes out, the sizes will match. So let's say d is a scalar, so this is a 1 cross 1. Let's say y is a n cross 1 column vector, and z is an m cross 1 column vector, right? So what is the shape of the derivative of d with respect to z? What is it? What is the shape of the derivative of d with respect to z?
It is the
Guys.
derivative of. Can
D with respect, d is a scalar, z is a vector. So what's it going to be, Kevin? 1 cross
D
n.
by n.
Right? That's what this is going to be, right? What is the derivative of, now y is an n cross 1 vector. What is the derivative of d with respect to y? What is the size? 1 cross n, right?
Yes.
And what is the derivative Jacobian of y with respect to z? What is the size? N cross m, right? Do these sizes match up? Do these sizes match up? When I multiply a 1 cross n vector with an n cross m matrix, I'm going to get a 1 cross n matrix. So as you can see, the whole thing just sits down just right. And that's why those shapes and sizes are so important. Everybody with me so far? Any questions? Yeah, okay. So,
Question?
yeah. So unless explicit Yeah, exactly. That's Raghav's comment, right? Thank you, guys. So, and so suppose I have something of this kind where I have z equals w y plus b and some scalar d equals where z is a vector and y is a vector. Then, and I have some scalar d which is a function of z. Then the derivative of d with respect to y is going to be the derivative of d with respect to z times the derivative of z with respect to y, where the derivative of z with respect to y is w. So this is why so is this equation making sense? So if I want the derivative of d with respect to z, this is going to be the derivative of with respect to y. This is going to be the derivative of d with respect to z times the derivative of z with respect to y, correct? And so what is this guy? What is the derivative of z with respect to y?
W.
W. And so you find that the derivative of d with respect to y is just the derivative of d with respect to z times w, correct? You guys with me? Yes? No? Right, okay. So now, what is the derivative of d with respect to b? What is it? What is the derivative of d with respect to b?
It's the derivative of d with respect to z times derivative to z with respect to b.
And what is the derivative of z with respect to b?
It's b.
That's the identity matrix, right? Times I, which is simply the derivative of d with respect to z. So this is beautiful, right? You understand this equation as well. Now there's one crazy equation, which is this guy. And now this guy doesn't follow all our standard rules for various reasons. Actually it does, but then to derive it through the standard rules is a bit of a pain. But we will show you, I'm going to sort of just stick it in your face and ask you to believe me. And so, where was this? This is the function now. So we're here. So here's where I am, right? Let me insert a new slide. And full screen. So I have d equals some function of z. Z is a vector. And z equals wy plus b, where y is also a vector. I want the derivative of d with respect to w. Now, in every case that we considered, we were getting the derivative up here before the delta y, right? But now when I'm thinking in terms of what is delta z times, I cannot write this as something times delta w. I can, but it actually ends up being tensor math, so it becomes very ugly. But then I'm just going to throw this at you, right? I have z, which is a vector. I have y, which is a vector of some other size. And then I have w, which is this cross this matrix, right? So if y is an n cross 1 vector and z is an m cross 1 vector, then what is the size of w? What is the size of w, guys?
N by M.
M cross n, right? So now, but then, so I have d is some function of w. Let me call this some whatever g of w. What is the shape of the derivative of d with respect to w? W is m cross n. What will the shape of the derivative of d with respect to w be? Jehan says n cross m. How many of you guys agree? What is the shape of the derivative of d with respect to w? So what did we say about the derivatives of scalars with respect to vectors and matrices? What was the shape? It's going to be n cross m. It's going to be the transpose of w. Just as, when we take a derivative with respect to a column vector, you got a row vector. when you take a derivative with respect to a matrix, you're going to get the transpose of the matrix. That makes sense? Same rule applied. Right. And so if I've got the derivative, so now let's consider this. How do I erase this thing? I don't know how to erase things. So let me write on this side of the board. Okay. So now I have d equals some function of some g of w. So you know the derivative of d with respect to w is, and so w is n cross m, say, or m cross n. Then this has to be n cross n, right? But if w is m cross n, then it knows that, then we know that y is n cross 1. Come on, right? Y is n cross 1, and z is m cross 1, right? We need these sizes for the size of w to fit, right? Everybody with me? The rest of you guys, I just have one yes. Are these sizes fitting? When I look, I don't think this. Okay, so now what is the size of the derivative of d with respect to z? What is the size of the derivative of d with respect to z? D is a scalar.
1m.
1 cross m, correct? So it turns out that the derivative of d with respect to w is going to be y times the derivative of d with respect to z. Okay? Can you check that the sizes match? Derivative of d with respect to w, what was the shape we wanted? The derivative of d with respect to w. N cross m. N cross m, right? And what was the size of y? What was the size of y? N cross 1. What is the size of this derivative? This one was 1 cross m, correct? You see that the sizes fit? Do you see the sizes fit? Right? And so we get this, I'm going to use this portion, that anytime I have a network of this kind, where I have some y, from which some z is computed, and from all these z's I have a divergence computed, then the derivative of the divergence with respect to this w is going to be this y times the derivative of the divergence with respect to this z. Does that make sense? It's the input times the derivative of the divergence with respect to the output. So this is, sorry, no. Is that right? I have this. Yeah. I've got, yeah, this one. Right? So the derivative of the divergence with respect to this weight is going to be the input times the derivative of the divergence with respect to the output. That makes sense? Everyone? And you will see the sizes fit. Is this what? Is this making sense size-wise? Everybody, tell me. Yes or no? Ketan, Vibha, is it making sense?
Yes.
Vibha, is that making sense?
Yes, yes.
Okay. And so there's a poll. I'm not actually going to ask you. Can you just take a look and answer me? If I'm given y equals f of g of h of x, where y and x are vectors and g and h also compute vector outputs, then what is the correct formula for the derivative of y with respect to x? Right?
Second option.
It's the second term, right? It's the derivative of f with respect to g times the derivative of g with respect to x times the derivative of g h with respect to x. So this is correct anyways. So now we have everything we need to compute the back propagation, right? We've already done the forward propagation. And so if y is a column vector of size n cross 1, what is the derivative of the divergence with respect to y? What is the size? What is this size? Guys, come on, I'm repeating 1 cross n, right? So we have a row vector over here, okay? And then I'm going to take a step back, and I'm just going to say I had z influencing y, influencing the divergence, right? So the derivative of divergence with respect to z is going to be the derivative of the divergence with respect to y times the derivative of y with respect to z, correct? Is it right? Making sense? And this guy is simply the Jacobian of this activation function. Yeah? Yes or no? And so I can say that if the derivative of the divergence with respect to y times the Jacobian of this activation function is going to give me the derivative of the divergence with respect to z. It's a trivial piece of computation, nothing fancy, right? Okay, now using the formula that we had earlier, this is Zn, this is Yn minus 1, and we know that Zn equals Wn times Yn minus 1 plus Bn, right? So what is the derivative of the divergence with respect to Wn? What was it? Using the previous rules that we saw. Guys, anyone want to take a guess? So I have this is my y, which is the input. The z is the output. There's a w over here, right? What is the derivative of the divergence with respect to this w? Using the rules that we just saw. So, Kevin, will the size match if you did it that way? We saw this earlier, right? How did we do this? What was this rule? Y times the derivative of the divergence with respect to z, right? And so this is going to be simply over here the derivative of the divergence. This is yn minus 1 times the derivative of the divergence with respect to Zn. And this is already computed. We got this in the forward pass. We got the derivative with respect to w. Everybody with me? Yes or no? You guys get it? Shooting. Did you get it? Okay. And continuing on, what is the derivative of the divergence with respect to Yn minus 1? What is it going to be? What is this going to be? Again, remember this formula. What is the derivative of the divergence with respect to Yn minus 1? We just saw the derivative with respect to w. But what about Yn minus 1? Guys? Hanin, can you tell me? What is it going to be? Anyone? Can I pick Jadev? Any answers? What will it be? This is going to be the derivative with respect to y is going to be the derivative of the divergence with respect to z, times the derivative of z with respect to y. Is that not correct? Vibha?
Yeah.
Right? Why are you questioning it? Y was used to compute Z, correct? You could also do it your way, but that's going to be much more challenging. Your answer is also correct, by the way, right? But you're going into derivatives with respect to matrices, it gets ugly. It actually becomes tensors. So this is what it would be, right? Make sense, guys? Right, and then what is this term? What is the derivative of Z with respect to Y? W. Correct? Awesome. And so I can say that the derivative of the divergence with respect to this Y is the derivative of the divergence with respect to Z times the derivative of Z with respect to Y, which is simply W. And this was already computed. We just write multiplied by W. Correct? Everyone with me? And of course, we also got the derivative of the divergence with respect to W that we saw earlier, which is Y times the derivative of the divergence with respect to Z. And we got the derivative of the divergence with respect to the bias. B is simply the derivative of the divergence with respect to Z. So I know it looks a little complicated, but there are very few formulae, right? So here's how I can do this. So at this point, I have the derivative with respect to Y, right? So then I can take a step back and compute the derivative of the divergence with respect to Z. And I'm going to multiply the derivative with respect to Y by the Jacobian of this activation, right? And then I can go back and I say the derivative with respect to this Y is the derivative with respect to this Z times the derivative of Z with respect to this Y, which is just the weight matrix. Making sense? So when I go back incrementally in this manner, I can go back all the way to the beginning. It may not make a lot of sense, but then, because I've packed on too many things. But here is the simple thing that happens. If I look at it in terms of pseudocode, at the first step, I'm computing the derivative of the divergence with respect to the output of the network, right? I have some layer, and then I have the next layer, then I have the next layer, and then I have my final output, and then I have my divergence, right? So the first thing I do is compute the derivative of the divergence with respect to the output of the network. And then I go back, and at each time, I get the derivative of the affine term by right multiplying the term that I already have by the Jacobian. And then, so I get the derivative over here at the input to this activation, whatever this may be, by right multiplying the derivative here by the Jacobian. And then I get the derivative over here by right multiplying this derivative by the weight matrix. You see what's happening here? I'm just alternately right multiplying by the Jacobian and then right multiplying by the weight matrix. I'm just going as I keep going backwards. So the derivative with respect to Z is the derivative with respect to Y times the Jacobian of the activation. The derivative with respect to Y is the derivative with respect to Z times the weight matrix. I just keep flipping back and forth, always right multiplying. Does that make sense? Yes or no? Yes or no? Right. So, and then somewhere along the way, you're going to get the derivatives with respect to the weights and the biases. Now, this equation, this figure, looks a lot more complex than it needs to be, because once I begin thinking in terms of influence diagrams and derivatives, so the first thing I can say is here, there's two simple rules. If I have an X, I have a Y, and let's say this X is related to Y through some weight matrix, and then Y goes through some scalar D, right? Then my chain rule says the derivative of the divergence with respect to Y is going to be the derivative of the divergence with respect to X. Is going to be the derivative of the divergence with respect to Y times the derivative of y with respect to x, which is going to be the derivative of the divergence with respect to y times w, right? It also says that the derivative of the divergence with respect to w is going to be x over here times the derivative of the divergence with respect to y. These are the two simple rules. We actually stated these rules explicitly. This guy, upper one, is simply going backward like so, and this guy is simply computing the derivative with respect to this parameter, right? You see this, what's happening here? Is this making sense? Folks. Okay, so here's what your network is going to look like. You have y0 influencing z1, influencing y1, influencing z2, influencing y2, and influencing z3. And let's just assume that y3 is my final output. This is influencing the divergence, correct? And so the parameters here are going to be w1, w, there's no parameter here. This is the activation function. This is going to be w2, there's an activation function. This is going to be w3, there's an activation function, and d, correct? So as I move back, I'm going here, and this is the derivative of the divergence with respect to y. Then when I go here, this is the Jacobian of y with respect to z. Then when I go here, this is going to be w, right? Correct? And then when I go here, this derivative is going to be the Jacobian. Then when I go here, this derivative is going to be w. Then this derivative is going to be the Jacobian. This derivative is going to be w. So as when I move back, I start off with derivative of the divergence with respect to y. I got this guy. Then to get the derivative with respect to this, I multiply it, right multiplied by the Jacobian for this edge. Then to get the, so now I'm here. Then to get the derivative with respect to y, I right multiply it with this weight matrix, W3, right? And then to get the derivative here, so now I have the derivative here. So then to get the derivative here, I'm going to right multiply this by the Jacobian. Then if I want to move back here, I'm going to right multiply this by W2. And then to get back here, I'm going to right multiply this by the Jacobian. And then to get back here, I'm going to right multiply this by W1. So as I go back, I keep right multiplying, right? And this is for the derivatives with respect to these variables. Does that make sense? Right? And then for the derivatives with respect to the variables, so the weights, it's always going to be y2 times the derivative of the divergence with respect to z3. Similarly over here, this is going to be, this is y3, right? Oh, no, y2. y1 times the derivative of the divergence with respect to z2. And this guy is going to be y0 times the derivative of the divergence with respect to z1. That makes sense? The whole thing? Right? And of course, the derivatives with respect to the bias is simply the derivative with respect to z. So everything works out. And so here is the pseudocode for it. So is everybody with me? Would the pseudocode make sense to you after this explanation? Okay. I'm not sure if it made complete sense, but that's how it is. So the network training algorithm in vector format is, you're going to compute for every training instance, you're going to compute the output and the divergence. Then you're going to go backward and compute the derivative of the divergence with respect to all the parameters. And then you average the derivative of the divergence with respect to the parameters by aggregating them and dividing by the number of samples. And this is your standard gradient descent rule. Now observe that I'm transposing the derivative. Why am I transposing the derivative? Anyone? Why am I transposing the derivative here?
The gradient.
To match the shape, because the derivative is transposed, right? And so that's it. When you're doing it in vector format, the code looks much, much, much simpler. This is just multiplication, right? At each point, I'm going back through the layers. I'm multiplying the previous derivative by the weight. Then I'm multiplying the previous derivative by the Jacobian. And they just keep going backward, by always right multiplying by a matrix. That's it. And so when I'm setting up for, say, a recognition problem, say digit recognition, is this 2 or not? I'd have a bunch of training samples with 0 or 1 labels. My network is going to be something with a simple sigmoid output. I can compute my KL divergence. I would use my back propagation to compute derivatives, and those derivatives would be used in gradient descent. If I'm performing digit recognition, I'd need to know which digit each image is. So my training data is going to look like this. Corresponding to each image, there's the actual label. And what would I do to this label before I begin using it? What would I convert this label to? Anyone remember?
One hot
hot.
vector.
1 hot, right? And so for each training sample, you're going to use the simple back propagation to compute the KL divergence and compute its derivatives going backward, and then use gradient descent to learn the network. And so that's it. That was today's lecture. The story so far: neural networks must be trained to minimize the average divergence between the output of the network and the desired output over training samples. Minimization is performed using gradient descent, and the gradients of the divergence with respect to network parameters can be computed using back propagation, which requires a forward pass of inference followed by a backward pass of gradient computation. The computed gradients can be incorporated into gradient descent. So that's it. Any questions? Any questions, guys? Jesus, Katrina, Abdul Munaim, any questions?
All is good.
No. Was this clear? Okay, then I will stop the recording.